Oh, I missed the deadline in a class that I took, and so
No way. It
by one
happens to the
minute,
best
by
of us.
1 minute, I'm like,
No.
I'm like the regular student here. I'm like, I thought, oh,
Right?
until midnight, and it was 11:59, and when I clicked enter, it was 12:00, and it said closed, and I'm like, oh crap! And I worked all day on it on Saturday. It's like, oh Lord. And now I'm hoping they still grade me, but who knows? But it's not that big of a deal. But it made me feel like how. So I wanted to make sure, if a teacher is really tough on the deadlines, don't be late. Because I know I'm not, I don't really, I'm that sharp on it. It's sort of a little bit of a, you can be late. It doesn't matter that much. But some teachers are really tough, I guess. So make sure if they are, don't play with it. Be serious about that deadline. All right. Anyway, that was just my experience a little bit. How are you all doing? Any questions? Any concerns?
No? Yes. Phyllis has a question. Yes, I have a question.
Oh, let me close my window. Sorry.
I just wanted to ask for clarification about the videos and adding them to the PowerPoint. How exactly does that work?
Yeah, so we are now in a phase where I'm looking at PowerPoints today. I'm doing some feedback giving on what you have. So I'm not immediately grading that as a grading. I'm going to start giving you points, of course, but I also want a little back and forth with that draft. So I give you feedback, and then most of the time, so far, what I've seen is feedback stuff is. Make sure the text is not in full sentences, for example, it's more bullet points I can actually share this thing with you real quick, that you make it so when you present, it's not like you're just reading text. Oh, let me see. This is the wrong PowerPoint. This one is the one I want. You can see that here. Make the text not too small. The 5-5-5 rule is pretty good. 5 words per line, 5 lines of text per slide, and 5 heavy text slides in a row. And so, especially the first 2, I think, are good to be a little bit aware of as we do the PowerPoints. Many of you do a great job. I'm just sort of like what I'm noticing in some of them so far. And so, yeah, not do full text, do like bullet points. So you can actually then in the video talk about what's on the slide. And so what I want you to do is put a lot of pictures in there, because when I try to do the video for my class, as you can see, I often try to explain a picture because it's just so much more like when I read about a pathology and there's just text, I can't visualize it as much. And often pathologies, they have signs, they have symptoms, they have things like that, that are nicely be seen on visual. The other thing is sometimes I like a little bit more detail. Like, for example, if you have a medication list of what to do as conservative medicine or conventional medicine, it's nice to get a little bit of why this medicine works, not just what is the name, because that just goes back out the window. And we all can do that on Google. That's boring. At the end of the day, but if we say like, hey, aspirin does do this to the blood, that's why it helps with such and such, and a little bit more the mechanism of action sort of behind it. That's what I found. Also, when we do describe the pathology, I would like to, let me see, I got one. I'd like to be maybe a little bit more detailed for some people. More detailed meaning like who gets the problem, more women, more men, what is the mechanism of the disease, what is a prognosis, how is he going to get better, is he not going to get better, how do people usually develop with that. So yeah, a little bit more, and how many people affects it, what is the date at the age range. So a little bit more detail on some, not all of them, just those are things that pick up. So when you go through it again, those are some general things to look for, I think, so far. And if you could actually, the other thing I realize I have to figure out sometimes who is doing which question. So if you could indicate that on the presentation, if you haven't turned it in yet, or as we go through it. and do a little back and forth. So you got that draft in for now, so that it's really good looking for a lot of you guys. Oh, and then sometimes to make when we do a video, and I'll get to your question. When we do a video, it's also nice to bring sort of a personal story in a little bit sometimes. Like, why did you choose, or why did your group who chose this disease to study? Oh, my grandmother had this, or I you know, a friend or whatever, or I just thought it's very interesting because of such and such. A little bit of that is also helpful, I think, to make it, because when we do the video, I would like you guys to do a group video. And at this point, it's developed really that Zoom is kind of a really good way to do that, because I think the Zoom accounts, and you tell me if not, then we have something else coming up, but they should be free, a basic Zoom account. So you can meet on Zoom, make a video, and share the PowerPoints with each other, like we're doing on Zoom here. And you can, then that should be the easiest process. And then that video should be about, I know altogether would be about 10, 15 minutes long or so. We have, or, you know, around 3 minutes-ish. Maybe, you know, at the end of the day, it's 3 to 5 minutes of what everybody presents. And so the videos will be about 10, 15 minutes. And then we upload those at the end, and then we watch each other's, a couple of each other's that seem interesting, and then we give each other a little feedback on it. We learn from that group, obviously. That's one reason why I'm doing that. But then in the same token, we can also give each other a little feedback and sort of learn, you know, have a learning where we point something out that is nice, and then we also can point something out that we feel like we could do a little bit better next time. And so that's how we also can learn, because a lot of us haven't done presentations that much, or haven't done these kind of things that much. And so that's the way, and we can talk about, Phyllis and Kantosha, how we should structure it. Maybe we can meet offline, or maybe we can meet after the session if the interpreter can stay. That way we can figure out how we should do the voiceover with you guys. Does that sound all right?
Yes.
Okay. Any questions?
Yes, I do. I have a question.
Yeah.
For the slides.
Yes.
Do you have a specific number of slides that you're expecting?
No, I mean, you think about, you know, per slide, it's probably about a 30-second thing. So I would assume it's at the end of the day about, you know, 5-6 slides per person at the end, because a lot of slides right now are text heavy. So you can space those out and make sure you do that 5-5-5 sort of rule, where you don't do too many lines on the slides. You make sure there's pictures on the slides, like not more than 5 ideas, or I would do less than that probably, you know. Most of the time it's a little more detail to add, and then it's spacing out and it's adding pictures to it. That's usually the general challenge. At least that's how that works to me. That's how I did my presentation for the class. First was all text, and then in the second semester, I started adding pictures. And then that process just never stopped, because that seems to be so much easier for people to understand. All right. And Google, that's great. That's why we did the exercise in the second week, to sort of how to extract a picture out of Google or any other browser, most likely. All right. Does that sensible? Yeah. Okay.
Yeah, that's great. Thank you so much.
Absolutely. Yeah. Anybody else has something that they want to talk about before we start going into some material?
Oh, yeah. In our presentation, Doctor, when we are sharing the slides, we are not sharing all the, we are not right all, right? We are just more images.
Yeah, you mean how to the presentation, how to do it?
Yeah.
Yeah, I like a lot of pictures. I think pictures are really helpful to explain things in this sort of way of how we're doing it. And then and then when you do the presentation, the Zoom, or you can do other ways too, but I think Zoom is just pretty easy. You share your slides and then you talk and show the slides like I do when I do the voiceover, or when we go now through some material.
Okay.
Okay.
Oh, thank you.
Absolutely. Well, good. If you can always interrupt me and we can go back to this sort of stuff. Again, here, just interrupt me if you have some questions or so, but why don't we, unless you guys don't feel like it, why don't we go through last week's material briefly and sort of review? Does that sound like a good plan?
I'm so pissed and I'm feeling
Uh-oh.
so overwhelmed.
Hello.
And frustrated at work.
Uh-oh.
That
Make sure you're not.
here today that I have
Let me
no
see. Somebody's not on mute.
over. And I kind of felt like this is fucking
All right. That's
Very good.
all right. Now we should be all right. So we do the endocrine system first. We started working with that. And did you guys fundamentally sort of understand how in the endocrine system hormones get secreted by an organ into the bloodstream, and then we go to specific receptors on the cells, and then the cells have a reaction to the hormone? Is that so fundamentally you guys understand that? Yeah, just talk to me, somebody, so I have a little feedback going on.
Yes.
All right, so that's good. So that's that really fundamentally how it works, because now we're going to go to the nervous system, and the nervous system in many ways works very similar, also in the fact that we have a chemical and we have a target cell that the chemical has a reaction on, like a muscle contraction, for example, or the initiation of the muscle contraction. But in the nervous system, the nerve impulse goes down a nerve, and then at the end of the nerve is where that process happens. That chemical gets secreted, and then the target cell is right there at that place. And in the hormonal system, in the endocrine system, the hormone travels through the bloodstream and sort of trickles down until it reaches the target cell that then has a reaction. And in that respect, it's a much slower system as compared to the nervous system. The nervous system is much faster acting, and we can actually have that here, the difference of the two described. And so that's why I kind of like the endocrine system going first here a little bit. We have glands that go into the bloodstream. Those are of the ones I just explained. What I just explained, that's the endocrine glands. This is why this is the endocrine system. Endo means inside, and crine means glands or hormones, something like that. And we have, on the other hand, the exocrine glands or crine glands, and those are sweat glands and sebaceous glands that give us the oily skin or the oily hair, for example. We have every sebaceous gland goes into a hair follicle and creates sort of an oily substance. The other one is also sweat, of course. And then we do also have intestinal glands, and those are also considered exocrine glands technically, because the intestinal system is going, from the mouth through a tube down to the butt, and so that's actually the outside world, so to speak. It's not the inside world. The inside world is where we have a membrane, covering the inside before we go to the inside, because we cannot bring, too much crap there. All right, so that's the fundamentals of that, and then as the other thing is, we have two types of hormones. We have some hormones that are fat loving. They have an affinity to fat, and some that are water loving and have an affinity to water. And through the cell membrane, through the phospholipid bilayer, we have that fat layer basically that the hormones need to travel through. And so the fat loving hormones, which are steroid hormones, those can go straight through the cell membrane, through that fat layer, and go into the cell and have a reaction on the inside of the cell. So the receptors of those hormones could be on the inside of the cell. The peptide hormones, which are the hydrophilic ones, the water affinity ones, they have to attached to a receptor on the outside, or that goes through the cell membrane, and then that receptor translates the message to the inside. And so we call those second messenger hormones, or they're triggering it through the second messenger system. That's that second messenger, and then here is then the last step here. And then that part on the inside does alter the cell function. Very often goes to the cell nucleus and triggers some production of proteins. All right, when we look at the hormones themselves, many hormones come from the pituitary gland. And that's right here. That's the thing that sits in the cella turcica. Remember the skull, the inside of the skull. And so that is actually that indentation there in the inside of the skull is then covered with a thick membrane, or I don't know how thick, but really strong, that goes right here. That has a hole through that nerve endings from the brain can go through into that gland and talk to that gland or have connections to that gland. But we want to make sure that the gland is separated from the nervous tissue, because glandular tissue is grows very fast. And we don't want, and is very strong that way, is epithelial tissue. And we don't want that to push into the brain, because the brain is very, very soft. When we're going to do the dissection in the lab in a few weeks, the dissection will be the first. I didn't quite pinpoint it yet, but we'll do the 1st of April. We're going to dissect the brain, and we're also going to dissect some eyeballs. So we'll do it after we.
The 1st of May?
The 1st of May, yeah. We have 2 more labs. We have 1 lab the 1st of May, and then we have the 15th. We have the kidneys that we can then dissect. And the 1st of May is the brain and the eyeball. So that then you'll sort of get to feel the texture of the brain. It's very soft. And so we don't want glandular tissue to push into it and press into the brain and harm the brain that way. So we cover it really with a strong membrane. So that's sort of one of the glands that has a lot of hormones that it secretes. Look at all these hormones that it secretes. But it is heavily controlled by the hypothalamus, which sits above. When we get to the brain, we're looking at here. This is from the side here, this is the pituitary gland down here. So that's that thing that sits in the cella turcica. And then up here is the hypothalamus, which is very close to it, but it's part of the brain. And we'll talk about that when we get to the brain. This week, I think. And the hypothalamus controls a lot of body functions that have sort of to do with appetite, temperature control, and a lot of these sort of functions, but it also controls the release of hormones. It has some hormones that it actually makes, and then it brings them down to the pituitary gland, and then the pituitary gland releases them into the bloodstream. Those are actually the ones down here. These are the nerves here. These are the nerves that go directly down, and then the hormone is secreted into the bloodstream. So this part of the pituitary gland is almost an extension of the hypothalamus. The front part is where the hypothalamus releases their own hormones, and then we have a little nervous vessels that go right through here and perfuse the front part of the hypothalamus. And the hormones that come out of the hypothalamus that go right into here influence the pituitary gland and tell that pituitary gland to secrete some of these hormones, more or less of them. And so we call those inhibiting hormones or stimulatory hormones. So that's these 2 functions. These like it secretes them, it tells them to secrete them, and then it tells them to stop secreting them. So the hypothalamus is really sort of the one that controls everything. And then the pituitary gland, we call that the master gland because it secretes so many hormones. And we're going to go through those hormones briefly. So here we first talk about the ones back here that the hypothalamus creates and then releases into the bloodstream directly from there. And those are antidiuretic hormone and the oxytocin. And the antidiuretic hormone, I also call it the anti-P hormone. And so when that's present, then you do not have to go to the bathroom as frequently. So the kidneys can retain more water that the bloodstream retains. When we, for example, drink caffeine, or alcohol, that hormone is suppressed, and that's why you got to go to the bathroom so much more, because the water just kind of flows out, because the hormone doesn't tell the body to retain more water out to kidneys, doesn't tell the kidneys to retain more water. So that's an interesting.
So sorry to interrupt. This is one of the interpreters. Marquise, do you mind turning off your video while you're walking? Just is a little bit visually jarring.
Oh yeah, that's sensible. Yeah.
We appreciate it if you can hear us. Thank you so much.
And then the secondary hormone is the oxytocin that comes straight from the gets created in the hypothalamus and secreted through the neurohypophysis. That's another name for that part of the pituitary gland, the posterior part. That's oxytocin. Oh, that's here. And oxytocin promotes uterine contraction and a milk ejection during breastfeeding. And so it's a hormone that we have when we have a baby. And it also is part of the sexual arousal, and sort of it's known as the cuddle hormone. So it helps us have nurturing and affectionate behavior. And so that's, of course, also important when we have a baby, but also important when we have a relationship and have loved ones. So those are the two hormones that come from the back part. And now we go to the front part and look at all of those hormones that go to the front. A lot of those hormones stimulate another gland, and then that gland secretes a hormone into the system. And then some of those hormones go directly into the system and do some work on, like the growth hormone, for example. Let's see where we are with that. So the first one is the growth hormone. Oops. The first one is the growth hormone, and the growth hormone is a good name. What I want you to know with this, basically, from now on, is kind of, I want you to know what is the hormone doing, and sort of have a little bit of a connection between the hormone and the function. And that's the stuff that I want you to have a parallel test review next to you, so you can look at the bullet points, what I want you really to know at the end for the test of the connection. I don't have that pulled up right now, but that's in the test review, the first bullet, I think. So the growth hormone increases cell size and cell division, and it mostly targets the bone and the muscle. So that helps our body to grow. That's the first one. The second one is the prolactin, and that goes into the helps the secretion of milk in the mammary gland. So that's lactin means milk, and so also in the male it enhances testosterone production, but it's mostly first was discovered what it does in the female, in the breast. So we called it the prolactin hormone. And then we got two of them. One is follicle stimulating hormone, one's luteinizing hormone. They act on the gonads, on the testes, and on the ovaries. And the follicle stimulating hormone stimulates the maturation of the follicle in the ovaries and promotes the sperm production in the males. So that's sort of, just sort of what I want you to know about that. The luteinizing hormone initiates ovulation and enhances the testosterone. And so that's function, of course, goes on both of the sexes. That's where we don't always have the same function between the two sexes. The adrenocortical hormone is an interesting, that goes to the adrenal cortex. When we look at the adrenals, we have an outside part of the adrenal and the inside part of the adrenals. Let's see if we actually talk about that down here. The outside part of the adrenal is the cortex, and that has multiple layers that then secrete multiple different hormones. And so those are aldosterone, has to do with blood pressure. Cortisol, you've probably heard of cortisone, it has to do with inflammation decrease, or we can decrease the pain because that way. And then a couple more, and then we have the adrenal medulla. And the adrenal medulla, the inside is where we get the sympathetic nervous system. So that we talk about that when we talk about the nervous system, but that's the nervous system that makes us alert and really active, and sometimes also agitated, because it's like the fight or flight system. And that gets secreted by the hypothalamus, but directly through the nervous system. And that in there, what we secrete is adrenaline. And you probably know what adrenaline does. you know, that's that edgy thing. Like you go down the freeway and somebody tries almost cuts you off, or you really react fast and then you get the jitters afterwards. If it's real bad, that jitters is the adrenaline. So that's an interesting place where you actually can see the difference between the endocrine system and the nervous system, because swerving out and making sure you don't have an accident in a precarious situation, that's the nervous system, that fast reaction. The adrenaline trickles into the bloodstream and you feel it like 30, 60 seconds later. That's the hormonal system. So you can see the sort of the difference between the two systems in that event.
I'm taking off those things fucking things.
Huh? Hello. Mute everything. Mute it. Mute yourself unless you talk. So that was the, where was I? Oh, I was at the right here at the adrenaline. So that's what that cortex, that's what we were talking. The cortex gets stimulated by the pituitary gland, the adrenocorticotropic hormone, trope. And so that's a long name. But adrenal, the cortex of the adrenal, and tropic means stimulating. Hormone enhances the hormone secretion of the adrenal cortex. That's the next hormone that the pituitary gland secretes, is the one that goes to the thyroid gland, and then it stimulates what's the thyroid hormone. So we can go right here to the thyroid hormone. The thyroid gland is the one in the front of the neck. And sometimes in the old days, people get a big knot front of the neck. That's called a goiter. And that was happening when the thyroid gland didn't function properly, because what we found out was because thyroid hormone needs iodine. And if it doesn't have iodine, then it's not going to function properly. And the thyroid hormone doesn't function properly. And the gland thinks like it has to make more and more of that, and gets bigger and bigger because of that. But it's non-functioning thyroid hormone. So that's why in the salt, you find iodine in the salt, because they started figuring out how it takes very little. So first they were really afraid, and because people would die if you give too much. But there was actually a place in Switzerland and a place in, I think it was Ohio, that allowed a research project to go forward. And if they found out how much that it takes, and so now nobody has really goiters anymore because of that. But anyway, the thyroid gland, sorry, I went all the way there, is a gland that stimulates energy production. And so it works with glucose oxidation and helps with the metabolic rate. So sometimes people that, you know, can't lose weight, for example, we're looking at the thyroid hormone and say like, hey, if there's a problem with that, the body's basic metabolic rate is not turned on. The basic machinery of the body doesn't work so well. So that could be a thyroid hormone problem. We go a little bit into how it's made in here. The details, you can look that up in the video. But we also have the two other hormones that come out of the thyroid gland, and those have to do with calcium. So those two hormones work with the calcium homeostasis in the blood, because calcium, as you learned with muscle relaxation, with muscle contraction, if you don't have calcium, you cannot have the actin and the myosin connect together. You need calcium in the blood. That's very, very important, and is also very important for many other functions. That's just one that tells you. And so it needs to be in a narrow range in the blood. So it's kind of like the blood sugar. The blood calcium is also very important. So we got two hormones that work. One increases the blood calcium level and one decreases the blood calcium level. And one is called calcitonin, and the other one is called the parathyroid hormone. And the way I remember that, how the function goes, the calcitonin tones the blood calcium level down. And so that's sort of my mnemonic that I use for that, has always been working. And you can see here on this slide, this is kind of nice. It's in the booklet too, how what it does if we have if we have to tone the calcium level down in the blood, we can put calcium into the bone. That's cool. We can decrease the uptake, and we can decrease the reabsorption of calcium. And we can also potentially get rid of more calcium. Well, we get rid of more calcium if you do that. So we just pee it out or poop it out. And then we have and this is another function of how the endocrine system works. We have an opposing hormone that does the opposite, because something that needs to be in an narrow range in the bloodstream either is too much or too little in order to be in the next. But we always push against it. And that's sort of where that negative feedback loop comes in that so often works in the body. We get out of a range, we got to push it back into the range. That's the negative. It's not negative, it's the opposite. So you should actually call it the opposite feedback mechanism. Because I had one class where I had to explain it it was really interesting. It was just so hard to get it as a concept. Negative feedback is not negative. It's just the opposing thing. Anyway, the opposite hormone here, we have this system in the calcium level, is the parathyroid hormone. And that name comes from, these are 4 little things here, these color things here, that are behind on the backside of the thyroid gland. And so when the people had a goiter, the people would take the gland out because it felt like that was a problem. Those people died because they also took that gland out, and then the calcium level was all out of whack. And so that didn't help. And so that's when they found out. And so that's why they named it parathyroid, next to the thyroid gland. So that's a pretty cool hormone. So that actually was that. We covered a fair amount of these hormones that come right out of the pituitary gland. And then we already went into the thyroid hormone. We already talked about the adrenocorticotropic and the adrenal cortex, what comes out of that, including the medulla. And see here, this is actually on this picture why this red thing goes straight down, because this is a nerve. This sort of indication is a nerve, and this nerve goes straight to the adrenal medulla, and the hypothalamus, therefore, with the nerve talks to adrenal medulla, but then the adrenal medulla is actually a gland and secretes the hormone into the bloodstream. So that's sort of an interesting place where the nervous system and the hormonal endocrine system work sort of together as one unit, because they are related the way they function. And so then we have other glands that do things. We have the pineal gland. And the pineal gland, if the hypothalamus is here, the pineal gland is a little bit to the back of that. This is the back side of the brain. This is the front side of the brain. So it's very close together. We'll talk about that when we go through the brain. And that is where we secrete melatonin, which is a serotonin derivative. And that we know that, a lot of us know that, is the day and night cycle, because we can take melatonin as a supplement to fall asleep easier. But also, when you go in the evening, when you get sleepy, that's the hormone that goes up. And so the movie is sometimes a little too interesting. So we don't go to sleep, and then we complain that we didn't have good sleep. But actually, if we're listening to our body, like, oh, I'm sleepy now, and then I lay down and go to sleep at that time, the body has its natural rhythm, which is not in tune with that much in our modern world, especially with these phones, obviously. Also, serotonin is important in the biological clock. It sort of helps the children start the sexual development. It's also good. It's also a good antioxidant, apparently. Okay, so that's the pineal gland. That's pretty cool stuff. And I like when I can feel what it does. Like, I'm falling asleep. Oh, my serotonin levels are high. Or I really have a hard time with falling asleep because my brain's going quack, and I have too much anxiety. And then I can maybe have a little melatonin to take. And that's, the body will be able to tolerate it quite well because it's just a hormone thing. The problem with that is if you take it all the time, the body will say, oh, I don't have to make it anymore. And then your body gets out of whack. So they recommend, if you do take it, don't take it all the time. Have breaks in it. Take, cycle around it. But that's fundamentally an interesting thing to understand, because if you give the body a hormone that the body actually itself makes and doesn't have to make it now, sometimes we have to because it can't. But if it doesn't have to make it now, then the body will also say, like, oh, I don't need to do it. The body's doing fine without me. And so be aware of that. I think some of the mechanism of some of the new diabetes medicines that also people use for weight loss, they work with that. They suppress sort of appetite, but then if you stop it, the body doesn't do it themselves anymore, and then that's partly why the weight goes up in these people and they stop it. Ozempic or something like that. I started doing a little research on that, so that's or started seeing stuff around it. Anyway, so that's pineal gland, and then we jump all the way down to the pancreas, and the pancreas is an interesting organ. It's around the small intestine, the first part of the small intestine, and it does a couple of functions. It does a lot of gastric juice secretion. So a lot of the stuff that digests your food comes out of the pancreas right here. That's, as I said before, an exocrine function, because the inside of the gut is connected to the outside world. So we call that the topological exterior. But in the endocrine system, what we discuss is the other thing that the pancreas does. It controls blood glucose level. So this is like with the calcium level, there is a hormone that brings it up and there's a hormone that brings it down. And so we know the hormone that brings it down, that's insulin. We got that plenty of times in the diabetes world, that we know if the body doesn't make insulin anymore, that body has to be given insulin, because you do not want that blood sugar to go wacko. Because, you know, if you compare water to Coke, Coke is very sticky. Water is sort of flows through. Blood with a lot of glucose in is very sticky. We don't like the sticky blood. That's going to cause all kinds of problems later, you know, if we do too much of that. Anyway, so that's, you know, of course, diabetes has a lot of things that we can help control as well. I try, you know, that sometimes when counseling comes in my practice, you know, especially if people are pre-diabetic, there's a lot that can be done. And if we can tap into something like, you know, maybe not, you know, too much sugary drinks, or more activity, or more vegetables, people like some, we get somewhere. The trick with changing lifestyle, I think, is, for me at least, is to find out what I can get rid of that doesn't cause me that much emotional pain, or what I can add that, you know, that I kind of like. And I always thought I just need to go jogging, because I'm like, that's, you know, the real sport. And I'm like, I don't really like jogging. I like hiking. I like walking. And it's like, that's fine. You know, I'm like, don't go overboard if you're not meant to do it, or you know, anyway, I just always want to say that those pieces too, when we say change your lifestyle, it's like, well, it's not that easy necessarily, but there's parts of it that we can include that are not that hard. And so I think if we start with that, and maybe I'm also a little over obsessive. So anyway, maybe it's easier for some of you than for me. So that's the pancreas. So the insulin brings the glucose level down. It decreases it, and the glucagon is the other one, and that obviously does the opposite. It brings it up, it raises it. And then lastly, we had is the gonads, and the gonads secrete mostly the sex glands. They secrete, in the female body secretes estrogen, in the male body secretes, the testes secrete testosterone. And here you got a whole bunch of function that does that. I just listed a whole bunch of function. But generally speaking, it develops the sexual characteristics, and then also the emotional maturity works with that, and it generates the germ cells and helps with pregnancy and lactation. So that's in general what it does. And then these are all the other effects that also come in. All right, good. That's that. That was a long chapter, a little bit long. You okay with that? Any questions? Then let's go through. The skin is actually not complex, really. I mean, it's obviously a very complex organ, but not for us. It's the parts are not that many that we work with. We look at that, you know, that's obviously the skin, the integumentary system is. We look at the top layer, which is what we touch when we scratch ourselves or so. That's the epidermis. That's a lot of layers of flaky cells that sort of create our leather. That's, you know, the leather. And then underneath it, we have the dermis. Epi means above. Dermis is then the underneath layer. If you cut yourself or you scratch yourself that you bleed, you went through the first layer into the second, because the first layer, the epidermis, doesn't have blood vessels. The blood vessels, epithelial tissue doesn't have blood vessels. So the blood vessels come right up to it and feed it from underneath, from the dermis. Also in the dermis, we have the hair follicles. And these are the hair follicles with the sebaceous glands that then the hair comes out of, all the body hairs, not just the ones on the head. We also have sweat glands. These are sweat glands right here going up. Are they? Yeah, they are. These things are sweat glands. These things are sebaceous glands. And then we also have a bunch of tactile receptors for the nerve. So when you touch yourself and you heat, you know, it's also pain, although pain are free nerve endings. Some of this, look, this is kind of cool. This is a nerve receptor that's like an onion. So it has layers. And if it's for depression, if you push down on the skin, some of these layers come together. And the more layers that come together, the more nerve impulse starts firing, the stronger the impulse. The nervous system fires by how frequently it shoots a nerve impulse down, like how frequently an electric shock goes down the cable. So an onion can coat that with a pressure. The more of the layers of, or these are not an onion, this is just layers of cell membrane, but the more of them come together, the stronger the nerve impulse, the more frequently the firing of a nerve impulse. So that's kind of cool. Anyway, I think that's cool. The dermis has an upper layer, we call it the papillary, lower layer, we call the reticular. The papillary layer are these like papilla, these dome-shaped things that stick out all around to increase the surface area, because that will brings the blood vessels right underneath the epidermis on top, tier on top, that then feeds the epidermis with nutrients and all that stuff. Because, you know, the epidermis, there's a lot of cells, because when this is all epidermal cells, you see this? And all of this up here is flakes, down here is not flakes. So the flakes means it's kind of dried out, they're dead. That's the leather stuff. But when I do this, a lot of these cells fall off already. I don't have to scratch. I just have to push on it. And which is great, because if you bang into something, if there's some friction, the cells just fall off, then you don't really have friction. From underneath, we make more and more of these cells, lots of them. And they are known to be stratified. That means multi-layer. Squamous, that means it's the flat cells. If you go back to the chapter 4, I think, and if you have the book, there's the first booklet in the tissue chapter. It talks about these different cells. And then keratinized means it has a protein keratin in, and that's a waterproofing protein. And it's the leather part of it, basically. So that's why we are waterproof. I thought that was kind of cool. Or SpongeBob, of course. When we look at the epidermis, it has multiple layers to it. So we have to start, you know, we have to name these things from like where the cells divide at the bottom. So you call that the basale or the germinativum, to then going up towards the surface of the skin, where at the end we call it corneum, because it's just cells. They're like little corns that fall off, flake off. We have a layer in there that's for the sole of the feet and the hands. There's a little thicker skin, call that the stratum lucidum. It's see-through skin. Then we have more the keratin accumulates in here in the spinosum, the prekeratin, and those are looking like spinies, although that doesn't look really like spiny. Well, maybe up here a little bit. But then those keratins, they dry out the cells and they become more granular looking, and so they call that granulosum. And basically that's the process. You make the cells, you make more keratin, more of that, you know, leathering, waterproofing protein, and then we dehydrate the cells, and at the end the cells are dead, so they can just fall off. So that's sort of the process. And these names you just have, you know, well, now you know what they sort of mean. We talked about, we have these most cells that make the keratin, we call them keratinocytes, if you need to give the cell a name. We also have other cells, the nerve cells that I talk about, the receptors. Some of them are called Merkel cells. And then the melanocytes, of course, are interesting. Those are making the pigment. So if we go and have the darkness of the color, the shades of the color are done by the amount of melanocytes. I mean, the amount of melanin the melanocytes secrete. You could think of them like umbrellas over the nucleus that protect the cell from being damaged by the UV rays. So that's it's actually a protective mechanism. That's kind of interesting. Langerhans cells, the long johns. This is German word. Long means long, and Hans means John. So I'm calling them the long john cells. They are resident presenting macrophages. So they are the monocytes that we just studied that go and sit in the skin tissue. They call them Langerhans cells there. So in each tissue, these cells have a different name because the tissue is discovered. A cell look like, oh, look, that looks like a different cell. So they give them a name, or the person who discovered it gives them their name, which is probably what this was about. Some German guy. That's just a slide of the skin. And then the dermis has that papillary layer that we just talked about, that pegs going up and down and bringing the nutrients to the epidermis. And then underneath is a reticular layer, and I'm just looking at them as like an anchoring layer to the underneath tissue. And that we have also the subcutaneous fat tissue below that layer. Then skin function. Just think about protection. First, defense. The stuff can't come in. That's the first line of defense. Don't let the crap come into the house. Take the shoes off. And that's actually a really good thing, taking the shoes off and having house shoes, not to bring crap in. We don't know what we're stepping on. Temperature regulation. We can bring the blood vessels closer or further away to the skin. That radiates off heat. So that's kind of interesting. Or preserves the heat also. Water balance. Look, the letter is not just from the outside, it's also outside in, it's also from the inside out. So we gotta, we're sort of having a letter skin around it that keeps that water in. And so the epidermis prevents a lot of water loss. And when we do sweat, though, we get rid of salt electrolytes, which is important because the ions, the electrolytes are charged molecules. They actually do multiple functions in the body. So we need to make sure. That's where Gatorade started being in Florida with the Gators, because they would sweat like crazy in Florida, and water alone doesn't make their function stay well. They get fatigued and crampy. And so then they started giving them electrolytes, which is what we started having with Gatorade. Of course, we have to be careful these days. There's so much sugar in that stuff, but it's the electrolytes that keeps our energy going. So that's what this stuff is about. Skin is also communication. If we blush, that's communication. So the face has the facial expressions. We talked about that already. And then we also talked about the sensory functions. So touch, temperature, pressure, even pain. And pain is actually a danger receptor. So when we feel pain, we retrieve. It's like there's danger there. So that's what that is really about it. Yeah. So that's kind of important to realize that pain and danger go together. Of course, chronic pain is, but it still has that same original place, because if we have chronic pain, the joints also need to be protected, and that gives us osteoporosis, for example, the stabilization. We talked about the glands, the sweat glands, the sebaceous glands, the hair. The hair has a few different parts to it. I don't know how detailed we actually gonna go there. But it has at the bottom, it has a papilla that feeds it. It has a bulb where it's growing, and then the follicle is where it sits in, and then we got the hair shaft. That's kind of the hair itself. And then nails, a very cool kind of thing that we have nails, not just to draw on them. Of course, that's also cool. But we have a plate. The nail plate is a hard surface where we can grab things with, so we can push against that hard part, and that helps us grab things. And so that's kind of the functionality of it. It's kind of cool. Good. So that's the skin chapter. Any questions to that? Yes, no, good. Keep going. I'm tired. Well, let's see. No, nobody says anything.
I'm tired and keep going.
I know, right?
It was straightforward. The nerves were interesting.
Yeah, so the nerves is, of course, and I wait till the end. But the thing with the nerves that are really sort of, when we look at the nerves, is we already talked a little bit about it. Now is the skin and the receptor, and we also talked about the endocrine system, the negative feedback loop. And so the nervous system is kind of a little bit like that. I mean, we have a feedback loop where we have functionally wise, we have a receptor that picks up some impulse from the outside. No, we're not talking about thinking right now. That's a little bit different. We're talking about communicating between the inside and the outside of the body. And also on the inside of the body as well. I guess I should start with that. That's what really the nervous system is. It's a communication system that controls and coordinates everything in the body. So that's inside and what's coming from the outside. So let's talk about the basic functioning as something comes from the outside. We poke ourselves, we got a pain receptor because the nerve gets irritated. We get a signal going up into the central nervous system, the brain, and the spinal cord. That's in the next slide. Oh, no, I can have it. Oh, here it is. The brain here and the spinal cord, that's the center where things happen, where we interpret what comes at it and where we make decisions of what to do with the information that comes at us. Everything else here, these are all just cables. And the cables have in them nerves that go into the brain or into the spinal cord from the that's known as the peripheral nervous system. I'm sorry, I'm a little scattered here. The cables are called the peripheral, what's on the periphery. And in the cables, we have nerves that bring information in and then also bring information out. So we have those two types of nerves. We call them sensory nerves and then motor nerves or impulse. Well, we could call them impulse nerves, but motor impulse is when the brain does something to the body, when there is a action happening. And then in the whole basic functioning, we have the receptor on one end, and then we have an effector on the other end. So the effector is what is being affected by the nerve. That is always actually a nerve, another nerve, that's usually inside the brain. A muscle, that's like if you get poked and it hurts, guess what you're going to do? You pull it away. Those are muscles. And also glands. That also gets stimulated by the motor nerves. Talked about central nerve, peripheral nerves here, the basic functioning. Yeah, that's a pretty good start. When we look at the nerve impulse, we're looking at electricity. Electricity are electrons in the cable. And electrons are negatively charged ions, really, or particles actually from the atom. But in the body, we have that represented in ions, because ions, if you remember the cell chemical thing, the ions are made when we have an atom not share an outer electron, but pull it away from it or give it to it. And so it has an uneven electron to proton ratio, and that makes them an ion. An ion is a charged atom, a charged molecule. No, it's not a molecule, it's a charged particle, really. And so we see here they're represented. Here's a sodium, Na sodium, and the plus means it has one too few electrons on it. But that means it's carrying actually a charge with it. And the charge is a positive or a negative. Then we get to magnetism. The positive want to be attracted to the negatives. The two positives, repel each other. Two negatives repel each other. So the positive always wants to go over the negative is the negative where the positive is from a electrical perspective. And so we can use that function together also with the fact that if we have concentrations of real physical particles, like a sodium is a physical particle or a potassium is a physical particle, that also becomes a concentration question. And so particles always want to flow from a region of higher concentration to a region of lower concentration. And so I could use those two concepts to now make a nerve impulse with it and then figure out how to do that, Well, the other thing that's important also, we actually need an insulator around where we do that function. So we need a boundary that things cannot just naturally cross. And that boundary at the end of the day is a cell membrane, because that's an oil film really. And ions are water particles. Ions are hydrophilic. They're not loving the fat. So they can't just penetrate the oil film. So the oil film becomes like the cable, the plastic around the wire. And so then what we can do in this situation now, what we can do is we can create a situation where we have a lot of sodiums put to one side, or some of the ions and in nerve impulse, we use sodium and potassium as those ions. We can have them pushed to one side of that cell membrane and the potassium to the other side of that cell membrane. And so then we physically have a thing of concentration established. And this is a pump, and pumps, we talked briefly in the chapter for cells. Pumps do that all the time. That's where you see this ATP. ATP means it uses energy. Energy means it goes against the concentration gradient. So that means it pushes sodium towards one side. It makes a high concentration of sodium on that one side. And the opposite on this is the outside of a cell membrane. And on the inside, right of the cell membrane, we do the same thing with the potassium. And when I talk about cell membrane here, I'm actually talking about all along a nerve. So this cell membrane here is all along that tube that a nerve really becomes. So when you look at the nerve, we'll talk about the nerve structure in a minute. The nerve has a cell body, and then it has a lot of extensions. That's how a nerve looks like. And the extension is also made of cell membrane. And this is the shell of that extension, of that tube. That's all along that tube we have this happening. Okay, and so that's very important, because when we ultimately get to a nerve impulse, what we really do is we now have this established inside and outside concentration. We have that established, and now we have channels in that membrane along that nerve, like all along the nerve right here. And when these channels open, the ions, those particles, want to go either into the cell or out of the cell, depending if they're the sodiums or the potassiums. So now we have this established thing where we have all along that nerve, we have all these channels. First, we have these pumps that continuously pump the sodium to the outside and potassium to the inside and make these high concentration areas. And now all we need to do is we have these channels in the cell, and they just need to open. So we have some channels, when they open, they let sodium go from the higher concentration to the lower concentration. So from the outside of the cell to the inside of the cell. And what they do, since they are charged, they're actually taking a lot of positives from the outside to the inside of the cell and change the relationship between how many positives and negatives are on the inside, on the outside. And that's known as voltage, the difference between the inside and the outside of positive and negative particles. That's voltage in electricity. And so when that happens, we change the voltage. And if we change that voltage enough, we make a nerve impulse. So it's the nerve impulse is made by bringing particles from one side of the cell membrane to the other side, and their chargedness, the charged part of the particle, is the second part, the electricity part, and changing that relationship, how much positive on the inside and the outside is, that makes the nerve impulse. So it's those two things. And so then, we bring a lot of positive from the outside to the inside, so we mess up that relationship. And then to stop a nerve impulse, we close those gates and we open the potassium gates, and we bring the same positives, but on a potassium, back from the inside to the outside, and the nerve impulse stops. Now, at the end of that, the chemicals are messed up, which is a problem, but we always have this sodium potassium pump running, and so it reestablishes that chemical gradient and brings the nervous system back to where it needs to be, and then it can send a next impulse down. And that's indicated here a little bit by this indentation here. So the first part, when we make the nerve impulse, we call that depolarization, because what we do when there's no nerve impulse happening, the inside and the outside is the outside is a little bit more negative, a little bit more positive than the inside. And so when we then bring the positive from the outside in, we change that relationship and make the inside a little bit more positive than the outside. And that part is called depolarization, because we're decreasing the the polarization, the opposite of each other. We make it narrower. And then when we close those gates and we open the gates that bring the positive back from the inside to the outside and make the inside more negative again, we call that repolarization, because we reestablish that polarity, that difference between positive and negative. And that difference between positives and negatives in electricity is called voltage. And here it just tells MV means micro voltage or millivoltage, sorry, milli. And then this here, this number 5 is the representation of that sodium potassium pump that always works and reestablishes then that chemical gradient again. All right. That's about it for a nerve impulse. Do you understand that a little bit better?
Yes.
Okay. Then lastly, what we have is just the anatomy part of the nerve. And that's this. And so that's much less complicated to figure out. Hold on. Yeah, the neuroanatomy. When I look at a nervous system as a whole, I have nerve cells, which is doing what we just described. And then I have, and so that was the nerve impulse. And then I have different parts of that nerve and a little bit more what goes on. And then I have supporting cells, and they call them neuroglia cells because glia means glue. And that's the neuroglia cells. So we have these two types. We don't really talk too much about the neuroglia cells in this class, but they do a lot of support stuff, which is kind of cool. And the videos go a little bit into it. The neurons are very different looking. Some of them look like regular neurons, the way that we sort of generically describe a neuron, but some of them look like that or like that. So there's different types of neurons. But in general, we have a main part, which is known as the body of the neuron, the cell body. They call that the soma, the pericardium. That's where we have the metabolic center. So the interesting thing with that is that I always found interesting. We have extensions. And on one extension, we have dendrites. They're called dendrites. Those are receiving extensions. So they actually receive other nerve impulses, or this is where we have the receptors for pressure or something like that. And those shoot also a little bit of a nerve impulse towards the cell body, but it is a little bit, it's not sort of reinforced the same way. It's like you put a pebble into the pond and it gives ripple effects. It's ripple effects as a visual. Because we actually have some other things stimulate a nerve, a dendrite, or they can also inhibit it. Inside the brain, you need to be able to modulate. And so there's these two, zeros and ones. One stimulates it a little bit more and one takes it away. So one makes the ripples, one takes the ripples away. And then we have the cell body. And in the cell body, we making chemicals a lot, and ATP and all that stuff, that metabolic stuff. And then we have a long extension known as the axon. And on the beginning here, we have a place called the axon hillock. And the axon hillock is a place where we initiate a nerve impulse. Because once we initiate a nerve impulse fires down the whole nerve. We call that the nerve. It's the whole thing, it won't be the nerve. But we often call the nerve the axon part, because the peripheral nerve is a lot of axons. And then at the end of the axons, we have extensions again, and we call that the axon terminal. And the axon terminal is where then the impulse comes down. All that, what we talked about, that nerve impulse. And at the end, it just releases a chemical from there onto the receptor of an next cell, which can be that another nerve, a muscle, or a gland that I mentioned earlier. So this is sort of how the endocrine system works. This is where the electricity works. And this part here is known as the axon hillock. And if the pebbles, the vibrations from here get strong enough, this initiates the nerve impulse. And once a nerve impulse starts, it cannot be stopped. It's a all or nothing event, it's called. It just goes and shoots down. You feel that when you hit the funny bone. That's when you feel that going down the finger. That's a nerve impulse if you hit the funny bone before. So those are the parts to the nerve that are important. This here talks about that end portion of the axon where we secrete the chemicals, and the chemicals goes into a space actually. It's actually a physical space. It's tiny, but it's still a physical space. They know that as the synaptic cleft. This is called a synapse, that connection. And then at the receptor, this could be a muscle, for example. We have the target cell, we have receptors that pick up that chemical, and then we will have a muscle contraction, as an example. We have a reaction happening, or we have another nerve impulse. This could be another neuron, and then that would be the dendrite. That would be like, oh, look, this is that little pebble that talks to the other neuron or says, no, 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 no. That's when we go and, try to solve a problem, how to figure out how to turn on the light switch or how to plan a vacation. So that's all sort of the fundamental way of how that works. So that's kind of cool. That's described in here, that process. I think briefly, I often talk about here about the neuroplasticity, because I think what's important about neuroplasticity, which is, the nervous system is very, very moldable and learnable and teachable. You can see that if you have a bad situation happening or something, it's really hard to, it's really easy to feedback more and more into that. And so that's happening with the thought. The more we do a thinking part, the more we do a thought, the stronger the thought gets. And what happens in the nerve, and I said before, nerves talk from nerve to nerve very often in the brain. We have a thought here. This is a thought. And if I create that thought over and over, it strengthens by having nerves grow back to the before nerves and then start feeding those ongoingly. And they call that a reverberating circuit. And so the stronger a thought gets, the more the stronger it becomes. The more we do a thinking, the stronger it becomes. If we don't do it, it decreases again. And so we can use that as learning of how the brain works, how the thinking works. And so that's sort of why it helps to, for example, do gratitude or have a gratitude journal and reflect back at the end of the day. What were the nice things? It could be a sunset or a sunrise, doesn't matter. It doesn't have to be a lot. What matters is what the brain is doing with it. And so the brain likes a good story. And so that's kind of interesting. And so that's fundamentally how neuroplasticity works. If you start hearing that, described more and more maybe in the psych world, but I think more generally, we talk more about that. When we talk nervous system, we also have to talk about the nerves themselves. We briefly mentioned we have nerves, sensory axons in nerves, and we have motor axons in nerves. Some nerves are just sensory nerves. They only have the sensory fibers in them, and some of them only have motor fibers in them. Most of them are mixed, so they have both sensory and motor fibers. For the word sensory, we can also use the word afferent, and for word motor, they also use efferent. I remember that as A is like an ascending, it's the same A, and that goes up to the brain. That's the sensory, and the efferent, I think of exit, and that goes away from the brain. So that's sort of how I remember that. I know these mnemonics. And then, inside the structure here, it gets very complicated. We have nerve. Well, it's kind of like in a muscle. We have a small axons, then we have wrappings around the axons, actually. And these are done by glial cells. And then we have multiple of those inside and then a wrapping around it. And that's called a perineurium. Neurium is a word for nerve covering. And the one on the inside is the endoneurium. And then we got a multiple of those fascicles together. And then surrounded is a epineurium around the whole nerve. So that's just a small to big structure. Interesting thing with the inside structure here, we have the axon, and we need we have coverings, fat coverings around the axon with spaces in between them. And those are areas, they're done by Schwann cells. That's kind of an interesting name. Those are areas where we speed up a nerve impulse, because where there is a Schwann cell, we cannot have that exchange of the ions. But when there is a space in between them, we can have an action happening there. And so what happens is we can have a nerve impulse speed up from point to point to point and sort of jump down the nerve instead of trickle down the nerve. So that's interesting. That's actually described, I think I jumped over that in the previous chapter. And that's pretty much it for that stuff. I think nerve generation is the last thing. We can generate a little bit of the axon, but it's very complicated, and very often it gets cross-wired, because there's so many of them. And so that can be a challenge, and really cut through a nerve. The cell body, we haven't figured out how to recreate that, if that's all broken. But the thing is, when we do amputations, what I want us to kind of think about is a neuroma. And people with amputations, it could be that there's pain at the end because those nerves just wildly grow around and they just fire, and that can be really painful. Anyway, that's about it for that. That's what I have. Is that helpful?
Oh, yeah, it was very good. Thank you. Yeah.
Okay, then let's finish. If, again, questions, just speak into me. Well, as long as I listen, I guess. I'm sorry about that. But let's just look at what we got going on this week. We did this stuff here. We don't have that test. That's a different class. And then this week is the brain. So the brain is a lot of labeling and coloring. So start with that early if you can. That will be helpful. And then we also have a gratitude journal that I want you to, I just talked about it, what we do with that. I basically want you to reflect back at the end of the day for 5 days and write 5 things down that you were pleased with the day, that was really nice, that made you heart warm, something like that. And then at the end of the 5 days, you kind of check in and see, hey, that was actually kind of cool, because often that stuff is like, people go like, how can that help? That's boring, thinking of that, or that I can't enjoy just a flower because that's just a flower. But it's like, no, those small stuff have a big effect in the brain. So that's kind of nice about that. So I want you to do that as you work your way through the brain, but make sure you start early on this stuff, because we do have quite a bit of terminology, I think. The brain is interesting, but it's also complicated. We got all these terms in the brain. All right. But I have a couple of videos as I go through it there. So that's hopefully helpful. All right. That's it. And then I think we have a little blood pressure discussion. So you guys just keep working on that. And I keep working on the presentations and give you the feedback. And we do back and forth a little. Then in a couple of weeks, we are going to make a presentation. Then you're going to start making a video on that. All right?
When is that video due?
I don't know. Let's look. That's a good question. And I probably have to adjust. Well, the video should be due. The video should be due week 15. And so then we can up it and finish up that week 16 with a discussion on it, looking at a few and give each other feedback. So that would be, I think the latest we can have videos going up will be the 14th, the Sunday before the last week. So these dates are a little bit off right now still. But
okay,
there's one extra week built into that. So